Hello everyone, this is Chao from CPAS Virginia Tech. In this video nugget, I will give a brief introduction to Simplified Optimal Trajectory Control for LLC Converter. Part 2, Soft Startup. Startup is a challenge in the control of LLC Converter. This is a result from commercial controller. The left top is time domain waveforms. Below is corresponding switching frequency during startup. The trajectory will be shown on the right. The red circle is a steady-state trajectory. At the beginning of a startup, the maximum switching frequency is 1.5 times resonant frequency. The initial point of a trajectory is 0 and 0. The first switching instant goes through an angle of half maximum switching frequency. The second switching instant has very large voltage stress. The third switching instant has very large current stress. These stresses will continue since the DC bias in resonant cap has not been built up. After some switching cycles, the trajectory becomes smaller and smaller. It takes a long time to reach steady state, and there are very large stresses during startup. Optimal trajectory control for soft startup was proposed by CPAS to solve the challenge. It is divided into 3 stages. The first stage uses asymmetrical current limiting band to settle resonant voltage DC bias. First, the high side switch is on. When resonant current touches positive band, the low side switch is on. When resonant current touches negative band, the high side switch is on again, so and forth until VCR equals half input voltage. The second stage uses symmetrical current limiting band to optimize energy delivery. As output voltage increases, the trajectory becomes larger, and stage 2 ends when VCR equals V in minus N times VO at a switching instant. Stage 3 is simply decreasing switching frequency until VO equals 12 volt. The trajectory becomes smaller and finally reach steady state. If a commercial microcontroller is used to implement OTC for soft startup by sensing the resonant current and comparing it with the current band, the digital delay will cause a problem. The dashed line is an ideal trajectory. When trajectory touches current band, the 0.8 microsecond digital delay will cause current stress to increase a lot. It would be more than 3 times larger current stress for 500 kHz LLC converter. Another switching instant, still very large stress. These stresses will continue. Digital delay will dramatically increase current stress. To solve the problem of a digital delay, simplified optimal trajectory control for soft startup with only sensing output voltage is proposed. For given output voltage, we can know the center for trajectory, and for given current stress, we can know the radius. So the switch frequency can be derived using these equations, and we can derive the switching frequency versus output voltage for given power stage. The maximum startup frequency for this 500 kHz LLC converter is around 1100 kHz. If the control is executed every switching cycle, it's good for up to 400 kHz. We can update PWM within 3 switching cycles. Then it's good for up to 1200 kHz, which is suitable for the 500 kHz LLC. So PWM can be updated every nth switching cycle to increase the maximum switching frequency limitation. This is a 500 kHz LLC converter. The input is 400 volt. The output is 12 volt. Matrix transformer is used for high output current application. The 60 MHz microcontroller only needs sense output voltage to achieve soft startup. This is a soft startup waveform under 0.175 ohm load condition. From top to bottom, the waveforms are resonant voltage, resonant current, and output voltage. The startup process is very fast, and the maximum stress is below 1.5 times full load stress. That's all for my video nugget. Thank you.